Sir, you are muted.
Thanks, Kandar. So, good morning. I hope I'm audible and the screen is visible. I also hope all of you have received your metal answer pages or whatever you can call it. Right? You've received your answer scripts for Vincent. Did anybody please confirm that? Okay. Just wait for a couple of minutes. Okay, maybe I'll just so the aim, as I've already told you in this class, is to show that any finite abelian group, right, can be shown to be isomorphic to product of cyclic groups, right? Again, just to recollect, every cyclic group is abelian, but every abelian group is not cyclic. But what we still can show is that give me any finite abelian group and I can show that I can basically break it down or decompose it into a product of cyclic groups. Okay, and the basic idea there is, so how many elements can a group have? In some sense a foolish question, but still, how many elements can a group have? Saying it is finite. So what can we say about the order of a finite abelian group? Anyone? So early in the morning, nobody wants to speak. Some integer, right? Say it is n. Are you aware of the fundamental theorem of arithmetic?
Yes, sir.
So what is it? What does it say?
Any number can be represented as the product of powers of the primes.
Right, right. So let's say the group, the abelian group that is given to you has order n. Then using fundamental theorem of arithmetic, we can sort of it implies that I can decompose n into a product of primes, say T1 R1 R2, so on, Tk Rk, right? And what do we know about these primes? That T1 to Tk are distinct primes, right? Okay, so what we are going to show is this group G. We are given a group G, whose order is n, and n can be decomposed into this product K R K. What we are going to do is we will show that we can decompose this particular group G into several subgroups, right? Let's call them G1 to G2, so on and so forth to GK. Each of these GIs is going to have an order P1 R1 of G2 is going to be P2 R2, so on and so forth. The order of GK is going to be PK RK. Okay, and so that G is basically isomorphic to G1 Cartesian GK, right? So each of these G's is going to have an order of some prime power. Okay, then what we are going to show is that each of these GIs, right, can be decomposed, or basically can be shown to be isomorphic, okay, to cyclic groups. Some Z to the power and ZAI. Notation. One I, so on and so forth. Then AN. Okay, so this is sort of the final result. Okay, each of these finite abelian groups, right, which has an order equal to some prime to the power some integer, right, will show that this each of these groups is isomorphic to a product of cyclic groups. And since the original finite abelian group is isomorphic to the Cartesian product of G1 to GK, eventually it basically means that G is isomorphic to something like this. Okay, that is,
Sir,
yes,
sir, can you repeat the last statement?
sure. Just a minute, let me finish writing this. Okay, so the aim is to show that any finite abelian group, right, is in some sense basically product of some cyclic groups. Okay, so G is isomorphic to product of some cyclic groups. How many cyclic groups, etc., that we are not stating anything. Okay, so the way we are going to prove this is in two steps. First, let's say the order of the given finite abelian group is n. Then using fundamental theorem of arithmetic, we know that n can be written as a product of distinct prime powers. Okay, so that is this step. Then what we are going to show is that I can decompose this group into a Cartesian product of some k groups, okay, where k is of course the number of distinct primes that participate in the decomposition of this integer n. Okay, and each of these k groups will have exactly PIRI numbers. Okay, so if I'm talking about the first group here, the number of elements in this group 1 is going to be P1 to the power R1. Okay, the second group is going to have P2 to the power R2 elements, and so on and so forth. The kth group is going to have Pk to the power Rk. Now, all of these groups are finite abelian groups, but they themselves may not be cyclic. Okay, right. If these were all cyclic, then we are done, but they may not be cyclic. Okay, then let's take each of these groups, Gi, I going from 1 to k. We will show that each of these constituent groups are isomorphic to some product of cyclic groups. Okay, once we show that, then since this is true for each of these constituent groups, so therefore it is also true for the original group G. Does that make sense?
Yes, sir. And sir, here we have group G1 to GK to be of order of P1 raised to R1. But sir, if we assume G1 to GK to be order of P1 and to
No, 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 no,
PK,
no. G1
then
is
they
of
will be.
order P1 to the power R1.
Yes, sir. I'm asking what if we assume them as a prime numbers, means order of them is P1 to PK, then they will be strictly
No,
cyclic.
no, but no, no. See, what does, so I've written here, right? P1 to PK, where P1 to PK are distinct primes. So if n is 8, I am not talking of that P1 is 2, P2 is 2, and P3 is 2. No, that's not what I mean. 8 is 2 to the power 3. That is what I mean. All
Yes, sir.
right? Right. So I'm not even sure whether I can accomplish so much in today's class. So, which is why I thought I'll just give you an overview of the proof. Then let's see how it goes. But I, personally speaking, I want to stop group theory today, okay, because there's so much in linear algebra to do. For sure, we are not going to finish all of that. Let me tell that right at the onset. But at least there's some point where we should start linear algebra. Anyway, so let's go ahead. I may skip some of the proofs, some of the simpler ones, uh, in order to sort of discuss the more complicated proofs in class. Okay, and there are a couple of proofs which are a little involved, so that is why we'll sort of skip some proofs, uh, do the complicated one, and then if time remains, we'll come back and do them. Okay. Okay. So, right, this is something we did in class last time. We described what is direct product of groups, right? So G1 and G2 are two groups. You can form Cartesian product of the sets, and on this Cartesian products, you can define group operation using the component wise group operations defined by the two groups. Okay, and the Cartesian product of the groups, which is itself a group, will be called direct product. Okay, and you can extend this to n groups. Okay, and so I have not written it over here. It comes later, but I think we did this, right? Extension to n groups. Okay. Similarly, we also have concept of sums of subgroups of an abelian group. Remember, we can talk of sums of subgroup only if the subgroups are of an abelian group. Okay. So H1 plus H2 is nothing but H1 H2. That is the more familiar notation. Okay? Just because the group is abelian and we decided to write the operation as plus, this H1 H2 will typically be represented as H1 plus H2. Okay, and this is what is called sum of subgroups. Since H1 and H2 are subgroups of an abelian group, they would be normal subgroups, and therefore H1 plus H2 will also be a subgroup of G. Okay, and then if G is equal to H1 plus H2, right, then every element G can be represented as a sum of two elements, H1 from the subgroup H1 and H2 from the subgroup H2. And we can say that H1, H2 is a representation of G. I'm going a little fast simply because we have done all this. In case you have doubts, please stop me. Then I think we looked at this proposition as well. So the question to be answered is, when is this representation unique? Yeah, and I believe Please let me know if I'm not right. I believe we proved that the representation is unique if the intersection of the subgroup contains only the identity. Okay, so this is an if and only if statement. If the two subgroups have the intersection equal to just identity, okay, then the representation will be unique. If the representation is unique, then the intersection of the subgroups will have only identity. And when that happens, we call the sum of H1 and H2, the two subgroups, a direct sum. Okay, and this is the notation. Okay, I hope all of you are with me till this point. Just a recap.
Yes, sir.
Okay, then let's get it started. So now we want to see, we have defined direct sum, right? We now want to see under what conditions is the direct sum of two subgroups equal to the entire group G. Okay, remember in this case we have just defined if H1 and H2 are two subgroups and if the intersection contains only identity, then the sum of H1 and H2 will be a direct sum. But we are now trying to answer when is G equal to H1 direct sum H2. Okay, is that clear? H1 direct sum H2 will be a subgroup of G, may not necessarily be equal to G. So it's important to see when will H1 direct sum H2 be equal to G. Again, remember, we began the lecture. What we want to do is to break down G into smaller groups. Okay, but the smaller groups, when put together, should give you back the entire group G. That is why this question is important. Okay, so this proposition states that if G is an abelian group with subgroups H and K, such that the intersection is only the identity, and the number of elements in HK, okay, this is not confusing, this is the same as HK. Okay, and if the number of elements in H plus K is equal to the number of elements in G, then G is equal to the direct sum of H and K. Okay, so that's the first part, and then of course it also implies that G is isomorphic to the Cartesian product of H and K. So how do we show that this is the case? Anyone?
Sir, last statement, that is G is isomorphic to H, Cartesian
Cross
product of H and K.
once again.
Sir, last statement is G is isomorphic to Cartesian product of H and K, not direct sum,
Yes.
right?
Yeah. So G is equal to H direct sum K. Okay, and this is isomorphic to H cross K. H cross K, of course, is not a subgroup of G.
Yes, sir. Okay, got
So how do we show that G is H direct sum K? Who wants to try this?
Sir, we already proved that direct sum of H and K is subgroup of G.
Right, but we now want to show that H direct sum K is the entire group G.
Yes, sir. And sir, it is given that the number of elements in H plus K is equal to number of elements in G.
So
So both are equal.
therefore G is equal to H direct sum. Right? The only subgroup of a group containing the same number of elements has to be the entire group itself. Okay, and how about the second part? to show that G is isomorphic to the Cartesian product of H and K? So what would be the isomorphism? I think it's easy to see. What elements would you have in H cross K? They would be tuples of this form, right? Where should phi, the isomorphism, map H, comma K2?
H direct sum K.
Oh, no, H and K, these H and K are elements.
Means yeah.
So I'm trying to find an isomorphism from H cross K to G.
H plus K.
H plus K or HK, I mean, using our usual notation. Right.
Yes, sir.
Right? Can you all show that this is an isomorphism? So is this a homomorphism? Let's just check. H1 K1, H2 K2. What would this be equal to? The definition of this is H1 H2 K1 K2. What would this be equal to? H1 H2 K1 K2, right? Since the groups are abelian, this would be equal to H1 K1 H2 K2, which is nothing but phi H1 K1 phi H2 K2. Okay, so phi is a homomorphism. How about 1 to 1 onto?
Sir, as H intersection K is the identity element, uh, that is why that will be means HK is it will be a unique representation of G. That's why it is 1 to 1.
No, once again.
Sir, as H intersection K is the identity element, that's why H plus K will be the unique representation
Why?
of G.
No,
Sir,
so
we proved it last
what
time.
did we prove?
Sir,
So
that
I want to show that phi is 1 to 1, right?
Yes, sir.
So
Yes,
okay.
sir. Sir means last time we proved that if H plus K is a unique representation of G, then
Mhm.
if and only if H intersection K is identity element. Here it is given that H intersection K is identity element. That is
Okay.
why H plus K is unique representation of
Right.
G. That is why if HK is equals to G and H1 K1 is G and G1 H1 K1 is equal to G is equals to H2 K2. This that plus H1 is equals to
Exactly.
H2 and K1 is equal to K2.
Good.
That's why it
Yes.
is 1 to 1.
Right. Right. So H1 K1 is a representation of an element of the group. H2 K2 is a representation of an element in the group. If both of them are representations of the same element, like as Tarang rightly points out, then the only way that can happen is if both the representations themselves are equal. Okay, so that is why phi is 1 to 1. How about on to? Where does that come
Number of
from?
elements in both are same, so
Exactly.
we'll be on to.
Right. Okay, so no, but number of elements in what? You want to show this, right? Okay, so where does this come from? Because we already know that for all group elements G, right, G is equal to some H plus K or HK. You want to use that notation. Okay, then phi of H comma K will be G. Okay, so therefore phi is ordered. Okay, so I hope this is clear.
Yes, sir.
Right, so one way to show that G is direct sum of H1 and H2 is to choose two subgroups, right, whose intersection is trivial, and the number of elements in the sum of these two subgroups, right, is equal to the number of elements in G. Now, what would be the relation between the number of elements in H plus K and the number of elements in H and number of elements in K? What is the relation between this and this?
So mod H plus mod K minus.
So why would it be mod H plus mod K, or number of elements in H plus number of elements in K? Is that right?
Yes.
No, that's not right.
Means
Tutorial
minus 1.
2, question 1. No, that's not right. See, this H plus K notation is confusing you. This is the same as this, right?
LCM of
No,
order of
no.
Order of H into order of K by order of H intersection K.
Exactly. And in this case, what is order
Order
of
of H
H
intersection
intersection?
K is 1.
Exactly. So, if you want to decompose the group G into direct sum of two subgroups, right? What kind of subgroups should you choose? One, of course, H1 intersection H2 would be just the identity, right? Second, because one is true, this into this should be this. Once you do that, then this clearly implies this, right?
Yes, sir.
Okay. Let's go ahead. So this is the direct sum of n elements. So in for two subgroups, right, we get a direct sum if the intersection of the two subgroups is identity. What about direct sum for n subgroups? Right? What should be the condition for sum of n subgroups to be a direct sum? That's the next question. When is H1 plus H2 plus so on and so forth Hn equal to the direct sum? Okay, so some of you may think that, for any two subgroups in this n subgroups, the intersection should be just the identity. If that is true, then the sum is also a direct sum. Right? But that is not the case actually. Once again, let me repeat this. So for two subgroups, we said that if the intersection contains only identity, then the sum is a direct sum. Okay, but for n subgroups, okay, if for any two of these n subgroups, the intersection is just identity, it does not imply that the sum is a direct sum. Does that make sense? Let me give you an example. Again, since we are moving towards vector space, maybe we take those examples. This is my subgroup H1. This is my subgroup H2. Okay, the x and y axis. What is the direct sum? Or what is H1 plus H2? It is nothing but H1 direct sum H2, right? Because the intersection has only identity. What is this equal to?
All whole plane, XY plane.
So R2. How about if I take this as H3, x equal to y line. That's my right. I hope all of you agree that this is a subgroup.
Yes, sir.
Yes. Okay. What is H1 intersection H2 and H2 intersection H3 and H1 intersection H3?
Origin.
The origin or the identity. So one would expect that the direct sum of H1 plus H2 plus the sum of H1 plus H2 and H3 would be a direct sum. That's the case. So what is the why is it not a direct sum?
Because H3 is linearly dependent on H1 and H2.
But Vandan, you are going into things that are not required and not defined. Why do you, in groups, right? There is no concept of linear dependence. Okay, you cannot define that word, doesn't, or that term has no meaning as of now.
So, sir, for means three subgroups H1, H2, and H3. First, we will take two of them, H1, H2, and we will see if their intersection is identity or not. If yes,
Right.
then we will check for H1 direct sum of H2 intersection H3.
Okay. So, what is it that we are looking for in a direct sum? What does direct sum give us?
Element of G can be uniquely written as
Uniquely written, right? That is very important. So, in this case also, I'm sure all of you agree that H1 plus H2 plus H3 is R3, right? But so in other words, I can represent any element of R2 as a sum of three elements, one from H1, one from H2, one from H3. But is that sum unique? So for example, 1 comma 1, right? I can write it as 0 0 plus 0 0 plus 1 comma 1. I can also write it as 1 comma 0 plus 0 comma 1 plus 0 comma 0. Okay, so you can see the issue here. The representation is not unique, even though this condition is satisfied. Okay, so this is not a direct sum. So for more than two groups, right, rather than intersection between subgroups being identity, right, we should look for unique representation. And that in fact is the definition of direct sum of n groups. Okay, so let H1 to Hn be subgroups of G, where G is an abelian group. We say that H1, the sum of these n subgroups, is a direct sum if for all elements H in the sum, H has a unique representation. Okay, that is the definition. Okay, and the notation is similar to the direct sum for two subgroups. So either something like this, or in short, you can also this notation. Any questions so far?
No, sir.
No. Okay. Then let's try to relate this definition of direct sum to the intersection thing. Okay, and right. So let G be an abelian group and let H1 to Hn be its subgroup. Then the following four statements are equivalent. I will just show all four of them at once. H1 to Hn, this sum is a direct sum, is the same as saying that take all subgroups except one subgroup, Hi. Okay, then the direct sum of the remaining subgroups intersection Hi must be the identity. Okay, and a more simpler condition is the third one. Okay, take any subgroup Hi. Okay, and sort of first of all, we are of course numbering all these subgroups from H1 to Hn. And take any Hi. Okay, in the order in which we have named the subgroups, take all subgroups previous to this I and compute their direct sum. If the intersection of this sum and Hi is equal to identity for all I, then also the sum of these n subgroups is a direct sum. Okay, and another way to check whether this sum is direct sum or not is the fourth point. It says that if the identity has a unique representation, then all other elements will also have a unique representation, and therefore that sum of subgroups will be a direct sum. Okay, so this point is interesting, right? The definition of direct sum says that all elements should have a unique representation. Right? What this point says is that even if the identity element alone has a unique representation, then you can show that all other elements will also have a unique representation. Okay, and of course, all of these H1 to Hn are subgroups of G, so all of them definitely contain the identity element. Okay, so trivial decomposition of E as elements of these n subgroups is of course E plus E plus E n times. Okay, that is the only way in which we can represent E as sum of elements from H1 to Hn, then that sum of these subgroups is also a direct sum. Is that clear?
Yes.
So I'm going to leave this proof as an exercise. It's not very difficult to prove this. Maybe later if time permits, and I don't think the time will permit, but still, it's not very difficult. I'm sure you can try it and you will get it. So let's move ahead. Oh, I think this is something we have already proved. So if G is an abelian group with subgroups H1 and H2, if G is the direct sum of H1 and H2, then G is isomorphic to the Cartesian product of H1 and H2. Right? That is just, I think, proposition 34, second part. So, part where we showed that phi from H1 cross H2 to G defined by phi H1 H2 equals H1 into H2 or H1 plus H2. Right? That phi is an isomorphism. Okay, so this we have already done. Okay, so let's move ahead. Same thing for more than two elements can also be done. Okay, so if G is an abelian group such that G is a direct sum of n subgroups, then G is isomorphic to the Cartesian product of those n subgroups also. And the proof again is trivial. N G, we define it as phi H1 H2 Hn equal to H1 H2 Hn. If we're using the plus notation, then equal to. Okay, and show that phi is an isomorphism. Okay, so yeah, I don't think there's much there. Let's move to. Let's now try to use the direct sums and Cartesian products in order to decompose an abelian group into smaller subgroups. Okay, so this is where we are now focusing on the main theorem. Okay, so let G be an abelian group of order e raised to r times m. Okay, and what is so special about P and M? P is a prime number and M may not be a prime, it can be a composite number. The only thing is that the GCD, okay, of P and M has to be 1. Okay, so they are indivisible. I hope that much is clear. Okay, before you read the next part of the proposition, try to relate this to what we are trying to prove. Okay, so what is it that we are trying to show? We're trying to show that we can decompose G into smaller subgroups. Okay, what is the order of any group? The only thing we are assuming is it's finite. Okay, now can you relate this equation 1 to the statement of the proposition that we are looking at?
Yes.
So n is the order of the group, and it can be, n can be written as P1 R1 into P2 R2, so on and so forth, Pk Rk. So what I can do is I can have P1 R1 and the remaining primes, right? I can multiply up together and get m. This would be my m. Would it satisfy the conditions of the proposition? In other words, would P1 and M be co-prime?
Yes, sir. It will
Yes,
be
sir.
Right? Because we had assumed that all these P or these K primes are distinct. Okay, so you can see the implication of this proposition without even going through the proof. So I am given a group of order n. N can be written as P1 R1 into some not necessarily prime number m. I can decompose this into two separate groups. Okay, that is what this proposition states. And moreover, the two subgroups into which we'll decompose, one of them will have P1 to the power R1 number of elements, the other subgroup will have m number of elements. Okay, what would be the next step? What do we do with m?
we will recursively again divide m
Exactly.
into.
Right. So induction. M itself is P2 into P2 to the power R2 dot Pk to the power Rk. So using induction, you can decompose that subgroup also into two smaller subgroups and keep on doing the same. Okay, so that is basically your first step. This was, I don't remember the number, it was 38, I believe. Let's just check. Yes. Okay, so if I'm given a group G, which is abelian, okay, remember that, of order P to the power m, where P is prime and does not divide m. Okay, then I'm defining two subgroups of G. Okay, and by the way, in the statement of the proposition, I'm just defining two subsets, H and K. What is the definition? So H contains all elements of the group G whose order is P to the power some S. Okay, where S can be any number between 0 and R. Okay, remember, this is a condition on the order, not on X. Okay, so if the order of X is P to the power some S, S between 0 and R, then that element is an element of the subset H. Okay, so that is one subset. The other subset is K, which consists of all elements of the group G whose order divide M. Right? Is the definition of the two subsets clear?
Yes, sir.
Okay. So then we can show that G is a direct sum of these two subgroups H and K. Moreover, H contains P to the power R number of elements and K contains M elements. Okay, so we're going to prove, and since the proof of this and the next proposition is involved, rather than working it out and making mistakes, I have written the proof in the slide itself. So the first question naturally is H and K are defined as subsets, right? For point 1 to hold true, we first need to show that H and K are subgroups of G. Okay, so why would H be a subgroup of G? Anybody? So what do we need to show in order to show that H is a subgroup of G?
H is group.
No, but what?
Closure and inverse.
Closure and inverse, or remember, would this, can H be an infinite subset?
No, so
No.
So
closure. Only closure. We have to check for closure.
closure, or I mean, there was this AB inverse, right?
Yes.
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 For all A and B in H, we need to show that AB inverse is in H. Okay, so let's try to do that. So what would be the order of AB inverse? Right? Remember, the condition for an element to belong to H is a condition on its order. Okay, so which is why I am looking for the order of AB inverse. What would be the order of AB inverse? It's an abelian group, right? That is also something we know.
So it will be LCM of order of A and order of B inverse.
And order of B inverse would be
Order of B.
B. Then what would this be? So this is nothing but LCM of P to the power sum S1 and P to the power sum S2. What would this be? P to the power
Maximum of S1 and S2.
exactly. Therefore, AB inverse belongs to H, which implies that H is a subgroup of G. How about K? Same thing, right? All AB in K, show that AB inverse is in K, or at least verify. So what is order of AB inverse? Same, right? LCM, order of A, order of B. What do we know about order of A and order of B?
They divide M.
So would the LCM of both of them also divide M?
Yes.
Yes.
Yes. So can I sort of leave that part as an assignment if you cannot do it right now? Is that fine? Then I'll just move ahead.
Yes, sir.
Oh, implies A subgroup of G. Okay, so good. Right? We have shown that these two are subgroups. Now we want to show that H plus K equal to G. Okay. For G to be equal to the direct sum of H plus K, we need to show two things. One is that G is equal to the sum of H and K. Second, H intersection K is the identity. Okay. So, first question is affirmative. Okay, yes. So now we know that GCD of P raised to R and M is 1, right? GCD of P and M is 1, so therefore GCD P raised to R M is also 1. So what does that mean? That means there exists integers U and B such that by combining P raised to R and M with U and B, we get the GCD, which is 1 in this case. Okay? I hope this statement is clear. Yes or no?
Yes, sir. Yep, yes.
Yes, sir.
Right. So then it's easy that to see that for every element G of my group G, G raised to the power 1 is G itself. Okay. So G can also be written as a product of G to the power UPR, UP to the power R, sorry, to be technically correct, into G to the power VM. Is that clear?
Yes.
What can we say about these two elements then? G to the power U into P to the power R. What happens if I operate G U P to the power R with itself M times? What will you get?
So we will get G raised to
Eh,
Vm.
No.
G raised to mu p power r.
M U P power R. What is M P power R?
Order of G. So it will be
Order of. So
identity.
Identity.
will be
Identity.
identity. So what can we say about the order of this element?
M.
Sorry,
M.
can you say it is M?
No,
Divides M.
divides
It
M.
divides M.
Divides M.
Oh yes, sir.
So
It divides.
what can we say about G U P to the power R? What sort of an element is this?
It
Look at the
belongs to K.
definition of K, right? This belongs to K, right? Because the order of this divides M. So therefore it must belong to K by definition of K. What can we say about G to the power Bn? If I operate itself P to the power R times, what will I get?
Identity.
Identity only.
Therefore, GVM belongs to
H.
H. So what have we shown? See, we took any arbitrary element of the group, right? So this has to be true for all G's. And what is this? This is nothing but the note. This is the same as this notation, GUPR plus GVM, isn't it?
Yes.
So we've shown that G is a sum of H and K, isn't it?
Sir, I didn't get the last statement. How that G raised to U, G raised to U P raised to R plus times G raised to Vm equal to G U P raised to R plus G Vm.
No, no, this is just a different notation, right? So remember the group is abelian, right? So
No, 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 sir. No, sir. My doubt is that
okay,
how G raised to U, G raised to U P raised to R equals G times U P raised to R.
G,
G raised to U P raised to R equals
uh-huh.
G times G plus U P
No,
raised
no,
to R.
no. So that's what. See, if I want to do A into A, right, I use notation A square, right? But if my group operation is plus, so how do I denote A plus A?
Yes, then 2A, yes.
2A. So that is what is happening. I am almost sure that I will be confusing several students, but I am myself confused between what notation should I use. I have been using a to the power m all the time in the course, but in this case it's an abelian group, so I should in principle use plus, but then if I suddenly change the notation, I might confuse you. So which is why I am trying to write both notations at the same time.
Uh, okay, sir, means it is G times U P raised to R is G plus G plus G U P raised to R times.
Exactly. Yes.
Okay, okay, sir.
Okay. So first thing we have proved, same thing, and the second thing we need to show is that the intersection of H and K is just the identity, right? So let's try to examine the intersection set. Let's say X is an element in the intersection of these two, right? What does that mean? That means that the order of X will divide P to the power R, okay, by definition of H, and by definition of K, order of X will also divide M. Okay, so what do we know about GCD of two numbers? Any number that divides these two numbers will also divide the greatest common divisor, right? That's the definition of GCD. Therefore, the order
Yes.
of X must also divide the GCD of this, but the GCD of this is just 1. So, X has to be only the identity. Does that make sense?
Yes, sir.
Because then I hope you see that we have shown that G is a direct sum of H and K. That's fine. Now, how many elements will these two subgroups have, H and K? G has P to the power R into M elements. How do we break this into two numbers is the question. So for example, can H have P to the power R minus 1 and can K have PM numbers, elements? That's the question.
No, sir. Then
No,
the
sir.
GCD will not be 1.
GCD of what will not be 1?
GCD of order of H and order of K.
Why should that be 1?
That should not be 1. That will not be 1. That will not be 1.
So what? Is that a problem?
Then H intersection K, we cannot say that H intersection K will be identity.
Why? Why can't you say H intersection K cannot be identity, the GCD of these two?
No, sir. Means it is not necessarily identity. Not necessarily identity.
But cannot say that it is not identity,
No, no,
right?
sir. I'm saying it is not necessarily identity.
Okay. Right. But so here is where I'm invoking a result that I did not prove in class. Okay. And apologies for that, but don't have time. So I'll just tell you what this theorem says. Okay. Cauchy's theorem says, so remember, if I have a cyclic group, right? Let's say G is cyclic of order n. If there is a number p that divides n, okay, will G necessarily have an element of order p?
No.
If G is cyclic, don't you think that will happen? See, if G is cyclic of order n, right, G is a group generated by A such that order of A is n, right?
Yes.
What can you say about the order of the element A to the power n by p? And A to the power n by p makes sense because p divides n.
So
What?
and that P is integer and it
Of
has
course, p
order
is,
P.
so this has order p, right?
Yes, sir.
Right. So for cyclic groups, You give me any integer which divides the order of that cyclic group, there will always exist an element with that order. But if my group is not cyclic, let's say it's just abelian, is it guaranteed? Will the same hold true for an abelian group?
No.
No, right? Again, so that's not the case for abelian group. Okay, but what the Cauchy's theorem says is the following. If G is an abelian group, and P is a prime number, okay, P is not any number, P is a prime number which also divides the order of the group. Okay, then the theorem guarantees that there exists an element A in G with order A equals P. Once again, let me repeat the statement of this theorem. We are not going to prove it. If G is an abelian group, not necessarily cyclic, okay, it can be any abelian group, and if you give me a prime number, okay, which divides the order of the group, then it is guaranteed that there will be an element in the group G of that order P.
Sir, P necessarily be prime or it
P
can
has
be
to
an
be prime. No, no. P is supposed to be a prime number. Only then it is guaranteed.
okay.
Okay? The statement doesn't say anything about composite numbers. It may or may not exist. But if P is a prime number and if it divides the order of the group G, then surely there will be an element in the group of that order. So, if you have understood this result, then can you try to think of why should the order of H be P to the power R and order of K be M? So for example, why can't the order of H be P to the power R minus 1 into L? This happens, what is the order of K?
P.
P. Can this happen? See, K is also a group, right?
Yes.
K is a group. P is a prime number that divides the order of K. P is prime and P divides P, right? What
Yes.
does Cauchy's theorem guarantee then?
There exists some element which has order equals order of K.
Exactly. There exists an element A in K such that order of A is P. Can that happen? What is the definition of K? The order of any element of K must divide M. But if the order of an element is P, can it divide M?
No.
No. This is a contradiction. Okay, so that is why the order of H has to be P to the power R and the order of K has to be M. Okay, let's move to sort of a very complicated result here. After this, before that, a small notation. Okay, this subgroup H that we worked out, this one. Yeah. Okay, it has p to the power r elements. Whenever this happens, okay, we will call that subgroup as a p group, okay, where p stands for this particular prime number. And if g is equal to h, we'll denote it. Sorry, the notation anyways for h is g e to the power r. If g is equal to h, then we'll say that g is a p group. Okay, so if let's say G has 2 to the power 3 elements, then G will be called a 2 group. And proposition 39 is basically recursion using proposition 38 recursively. Okay, so if G is an abelian group of order p1 to the power r1, p to the power r2, so on and so forth, pk to the power rk, okay, where p1 to pk are distinct primes, then G can be shown to be a direct sum of G pi ri, okay, where the order of each G pi ri subgroup is nothing but pi to the power r. I hope you see this is, I'm not going to prove this. In fact, there is nothing to prove basically. You just use induction and proposition 38. Let's go ahead. This is where cyclic groups come in. Okay, if I manage to explain this proposition, I think we are done. I can see I have about 4 minutes. Please give me about 10 minutes. Right? I hope I should be able to do this in 10 minutes. Okay? So what does this proposition state? Let's say G be a finite abelian P group. Okay? Please be careful here. I'm making more assumption more than abelian. And again, let me connect this to the first slide where I gave you an overview. Okay, so 38 and 39. It tells me that I can decompose G into a product of K groups. Each of these K groups has Pi to the power Ri elements. So each of these is nothing but a particular Pi group. Right? I hope that is clear. Now,
Yes, sir.
let us take each of these Pi groups. What we want to now show is that as of now, this GI is just an abelian group, not cyclic. So we now will go ahead and decompose this P group into a product of cyclic groups. Okay, so that's proposition 40. So that's the proposition say. If G is a finite abelian P group where P is a prime number, then I can decompose G into a cyclic group generated by some element A, and it's not just any random element A. That A is nothing but an element of the group G which has the maximum order. Okay, so you have a finite abelian group, so of course there will be some element which has a maximum order. This may not be unique, but there surely exists an element which has the maximum order. Take that element, generate the cyclic group that is generated by that element. That would be one subgroup, and there would be some other subgroup denoted by H over here, such that the direct sum of these two will be equal to the group G. Okay, again, Before we look at the proof, what happens if we recursively use this? G is some A1 direct sum H. Then
So we can write H as
exactly.
A2 cross A2 direct sum K, where A2 is the element of maximum order in H.
Right. And so on and so forth till you basically get this. Some A. And this we know is isomorphic to A1 Cartesian A2 Cartesian AK, which is what we want to show. Right? Each of this is a cyclic subgroup, right? Is it clear?
Sir,
Yes.
sir, what if element A has maximum order equals to order of G?
Yeah, so that's the simplest case. And in that case, what will happen?
Means, sir, I mean that it will always happen.
No, why should that happen?
Means we have group G, which is P group, means its order is P raised to some R.
Right?
There, so there should be element which has order equals to P raised to R.
Take this group. Z3 Cartesian Z3. What is the order of this group?
Nine.
9. So give me an element in this group which has an order 9. If that were the case,
One
then
comma two.
1 comma 2. Okay. Can somebody find the order of 1 comma 2 in Z3 cross Z3?
3.
Order is 3.
Yes, sir.
Okay. So order of this is not 9. Okay. In fact, there was this theorem that said that Zm cross Zn is equal to Zmn if and only if ECDMn is 1. If that were to be the case, then you would have saved me several hours of work, Vandan. Because if there is an element A of the order P raised to R, then what is G?
Cycling group.
It is itself
It's a
cyclic.
cyclic group. So I don't need to do anything then. Each of those P groups is itself a cyclic group. I need not decompose each of those P groups into product of cyclic groups. Okay, so but I hope I've convinced you the fact that if I have a finite abelian P group, I may not have an element in it with the order equal to the order of the group. Okay?
Yes, sir.
Okay. Right. So order of group is, let's say, some P to the power n, simply because G is a P group. If n is 1, then the order of group is equal to a prime number, right?
And
And
it is
we have
cyclic.
already, exactly, it is already cyclic. So G is the subgroup generated by A, and I can write G as this, direct sum this, and I'm done. So let's look at the case where n is greater than 1. Here we'll be using induction. So if the group G has order p to the power n, I'll assume that the statement is true for all k less than n. Okay. So let us pick, as the statement says, let us pick an element A in the group G with maximum order. Okay, but since the group G is a P group, right, the maximum order will be P to the power some R only, where R can be, of course, between 0 and n, right? Remember, the order of an element divides the order of the group. The order of the group is some prime to the power n. So therefore, the order of any element would be of the form p to the power r, where r is between 0 and n. And I don't want, of course, A to be the identity element. Is this statement okay?
Yes, sir.
Yes.
Now R, if it is n, then we are done, as we just discussed. G will be cyclic, right? So we'll assume that R is strictly less than. Okay. Then let's pick another element B in the group, which is not in the subgroup generated by A, and from the remaining elements, B has to be an element of the minimal order. Okay. A is an element of the group with maximum order. B is an element of the group which is not in the subgroup generated by A and is of minimal order. Okay. And then let's look at the subgroup generated by B and then try to see what is the intersection between these two subgroups. Okay. Should we stop here? I mean, is it a bit too much? If that is the case, then let me stop here. This is going to take about 10 minutes more. Let's do one thing. I will record the proof for this in a separate video and share it with you on the course website. Before we meet on Friday, you guys can go through the video and then we can discuss your doubts, if any, in the next class. Would that be fine, or do you want me to go ahead with the proof?
Okay, sir. It will be fine.
Okay, so if Vandan is tired, yes, several
No,
others
sir.
are tired.
I can do this for 15-20 minutes, but for others.
Right. Okay, so I'll record the proof for starting this proposition and whatever little is left. There's not much left, right? And you can go through the video and let me know at the beginning of the class on Friday. But I positively wish to begin vector spaces of linear algebra on Friday. Okay? That's the only reason why I'm sort of rushing through this a little. The proof is something that you should see once in your life, and maybe if you go on and study proper math, you will need to relook at the proof once again, but otherwise you don't really need to know all the details of the proof. Okay? In this week's tutorial, we'll have examples based on this. We'll take groups of certain orders and see what could be the cyclic subgroups into which this group can be divided. Okay, so with that, I'll stop for today and see you guys on Friday. You will get to know your projects hopefully no later than tomorrow morning on your Moodle website. Okay, so we have discussed and decided all the projects. We'll assign it. At least I will assign it to all of you using Moodle. Thank you.
Sir, will projects be in groups?
Yes, so group will have 10 students each.
Okay, sir.
ID wise,
ID wise, yes.
uh,